the ground beneath your feet isn't just, a static layer of dirt and solid granite.
Right. Not at all.
It's actually a multi-billion-dollar mystery. I mean, we're talking about microscopic oceans, trapped gases, and just extreme pressures hidden miles below the surface.
It is a completely alien environment down there.
Totally. So today, you and I are going to figure out how scientists actually read the hidden story of the deep Earth.
Yeah, we're looking at some really foundational petrophysical science today.
Exactly. We are diving into a highly specific framework used by professionals. We're drawing from the inaugural field guide of Petrophysics Daily to understand exactly how this invisible world is measured, mapped, and interpreted.
It's a great field guide. It really breaks down the complexities.
It does. So, okay, let's unpack this. What exactly is the day-to-day reality of petrophysics? Because, from the outside, it just looks like a black box of impossible math and guesswork.
Well, it can absolutely look like a black box if you don't know the rules of the game. Petrophysics isn't just about identifying rocks or, finding oil. The source defines it perfectly. It's the integrated interpretation of rock, fluid, and measurement data.
Integrated interpretation, okay.
Yeah, you have to understand that we are operating completely blind. I mean, we can't take a tiny submarine down into a microscopic pore space 3 miles underground.
That would be cool, but yeah, impossible.
Right. So we have to reconstruct an entire physical environment using indirect signals, which means we are constantly fighting against uncertainty.
And that concept of integrated interpretation is doing a lot of heavy lifting here. It implies that nothing in the subsurface exists in isolation.
Exactly.
And for those of you listening who already follow geology or engineering, we aren't just dealing with a dry, solid block of stone. The rock has a matrix, and it has a pore system.
Yes, the container.
Right. I can think of it like a rigid microscopic sponge holding liquid. But the glaring problem here is that those pores are already occupied, right?
Oh, they're actively occupied by fluids, water, oil, gas. And, well, this is the fundamental challenge of the discipline. Because the rock properties, like porosity and permeability, that's the physical architecture. They describe the reservoir itself.
The sponge.
Exactly, the sponge. But the fluids fundamentally alter every single measurement we try to take of that architecture. You lower an instrument down a wellbore, and that instrument is firing signals into a fluid-filled matrix.
Wait, if the fluid is constantly altering the signal, how do you ever isolate the rock's actual properties? I mean, aren't we just perpetually measuring a contaminated signal?
What's fascinating here is that we don't try to isolate them.
You don't?
No, the golden rule established in our field guide is that interpretation is mathematically and scientifically stronger when rock and fluid controls are reviewed together.
Oh, I see.
Yeah, you don't try to mathematically subtract the fluid to find the dry rock. You study the interaction.
Because they affect each other.
Right. The fluid changes the signal in predictable ways based on its density and salinity. So by understanding the fluid behavior, you can basically reverse engineer the rock's physical properties.
So you have to model the container and the contents simultaneously.
Continuously and simultaneously. If you try to separate them, your entire model just collapses.
Wow. But the deeper you go, the more complex that interaction becomes, right?
Yeah.
Pressures change, temperatures spike, fluids mix.
It becomes incredibly chaotic.
So to handle that much chaos without just, guessing, you need a rigid framework.
Right.
And this is where the field guide introduces a very specific review path. It's like a hierarchy of controls.
The traceability sequence.
Yeah, it lays out 4 checks. But what really caught my eye is that it assigns very specific weighted percentages to these checks.
The cascading percentages, yes.
Yeah. Rock properties at 92%, fluid behavior at 84%, core and logs at 76%, and geological context at 68%. So what does this all mean? Like, why these specific cascading numbers?
Well, those percentages represent a hierarchy of confidence and foundational necessity in the review path.
Okay, break that down for us.
Think of it as a structural dependency tree for your interpretation. You start at 92% with the rock properties because, this is the physical absolute.
The actual rock itself.
Exactly. If you misunderstand the basic physical nature of the rock, whether it's sandstone or limestone, for instance, every single subsequent calculation you make will be exponentially wrong.
Oh, wow. So it's the foundation.
It is weighted highest because it is the baseline reality of the container.
Makes sense. Then you step down to 84% for fluid behavior.
Right. You are layering in the dynamic variable. Once you know the rock, you apply the 84% check to see how the specific fluids in that environment are behaving.
And how they alter the signal.
Crucially, yes, how they're affecting your tool measurements downhole.
Okay, and then we hit 76% for core and logs. But I want to pause here for a second.
Sure.
Because the jump from fluid behavior to core and logs feels like a jump from a physical state to like a methodology. Why is this sitting at 76%?
Because this tier is all about reconciling scale, which naturally introduces a new layer of potential error.
Reconciling scale.
Yeah, so you might have a physical core sample pulled from the well, an actual cylinder of rock you can literally hold in your hand in a laboratory. Okay. That core gives you microscopic, highly accurate data, but you only have a few feet of it.
Right. It's a tiny sample of a huge well.
Exactly. Well, logs, on the other hand, scan thousands of feet of the well bore, but their resolution is much, much lower.
So you have to make the match.
Yes. The 76% control is the rigorous process of forcing your microscopic core data to mathematically agree with your macroscopic log data. If they contradict, your interpretation fails the check.
That is so strict. And that brings us to the bottom of the cascade. Geological context at 68%.
The final check.
Yeah, and I have to push back on this placement a bit. Putting geology at the very bottom of the list at 68% seems completely counterintuitive to me. I mean, isn't geology the entire reason the rock is there in the first place? Why is it weighted the lowest?
It's a great provocation, but don't confuse the lowest percentage with the lowest importance.
Okay.
The 68% weighting reflects its role as a boundary condition rather than a direct real-time measurement.
A boundary condition.
Yeah, so rock, fluid, and logs are real-time physical data points you're analyzing from the wellbore today. But geological context is the historical regional model.
Oh, I get it.
The field guide explicitly states that geological context defines what the interpretation can and cannot claim.
Ah, so it's the ultimate reality check.
Exactly. If we connect this to the bigger picture, imagine your calculations on the rock, fluid, and logs spit out a porosity of 25%.
Which is good.
That looks fantastic on paper. But if your 68% control the geological context tells you that this specific formation was compressed under glaciers for 1 million years.
Oh boy.
Right. It shouldn't physically be able to exceed 10% porosity. So you have a massive red flag.
Because the math says 25, but the Earth's history says that's impossible.
Precisely. The geology bounds the math. It stops you from projecting physically impossible scenarios just because an equation gave you a nice number.
That makes the framework incredibly robust. But, you know, we've been dancing around the actual tools themselves.
That's the fun part.
Yeah. We know we're looking at a wet rock sponge, and we have the rules for how to weigh our confidence. But the glaring problem is that this rock is thousands of feet underground.
Right.
So how do we actually gather this data? Because this is where the industry just throws an alphabet soup of acronyms at you, like GR, RES, DEN, NPHI, US.
The well log suite.
Yes. What are these things?
These are the instruments we literally lower into the borehole on a wire line to send signals back to the surface. And you're right, to an outsider, it just looks like a screen full of chaotic, squiggly lines.
It totally does. Like an EKG for a rock.
That's actually a great analogy, but this is where we have to separate direct evidence from interpreted evidence. The squiggly lines are downhole tool responses. They are interpreted evidence.
Let's actually unpack how these work, because it's not just magic. It reminds me a bit of using sonar in a submarine, you know? Well, you bounce a sound wave off a canyon wall, and how fast the echo comes back tells you how far away it is. These tools are doing something similar down the well.
Right.
They are shooting energy into the rock, and the echo, or the resistance, tells us about the formation.
That is the perfect way to look at it.
Awesome. So let's take GR gamma ray. What is that actually doing?
Well, gamma ray is actually a passive measurement. It is essentially a highly sensitive Geiger counter lowered into the Earth.
Wait, really? Just a Geiger counter?
Yes. It measures the natural radioactivity of the rock.
Okay, but why do we care if the rock is radioactive?
Because shale, which is a very tight rock that traps fluids and completely ruins permeability, happens to contain radioactive isotopes like potassium, uranium, and thorium.
Oh, wow.
But sandstone and limestone, which are great reservoir rocks, generally do not.
So that one squiggly line instantly differentiates the useless rock from the valuable rock just by listening to the natural radiation. That is so clever. What about RES, resistivity?
Now, resistivity is an active tool. It pumps an electrical current into the rock formation and measures how hard it is for that current to travel through.
Okay, so pushing electricity through the rock.
Right. And this goes right back to our fluid behavior control. Salt water, which is ubiquitous deep underground, is highly conductive.
Makes sense.
So it has low resistivity, the current flows easily, but hydrocarbons, oil and gas, they are electrical insulators.
Oh, they have high resistivity.
Exactly.
So if your gamma ray says, hey, we are in a great sandstone, and your resistivity suddenly spikes off the chart, it's telling you the fluid inside, that sandstone isn't conductive saltwater. It's oil or gas.
You've got it. You are combining two completely different physics principles to map an invisible environment.
This is amazing. Let's keep going. DEN and NPHI density and neutron porosity. From what I understand, these are often run together, and they are a bit more aggressive than just listening for radiation.
Much more aggressive. The density tool actually fires high-energy gamma rays into the rock formation.
Oh, wow, so it's shooting them out now.
Yes, it bombards the rock. And the denser the rock matrix, the more it absorbs or scatters those gamma rays. By measuring how many gamma rays bounce back to the tool's detector, we can calculate the bulk density of the formation.
Okay, and then the neutron tool fires neutrons into the rock, right?
Yes. It emits fast neutrons. Now, this is where the physics gets really cool.
All right.
Neutrons are roughly the same mass as a hydrogen atom.
Okay.
So when a fast neutron hits a heavy rock molecule, it just bounces off and keeps its speed.
Like a pinball bouncing off a bumper.
Perfect analogy. But when it hits a hydrogen atom, it loses a massive amount of energy. It's like a billiard ball hitting another billiard ball of the exact same size.
It transfers the momentum.
Exactly.
And where is hydrogen hiding underground? It's in the water and the hydrocarbons. It's in the fluid.
You've got it. So the neutron tool is fundamentally hunting for fluid by hunting for hydrogen.
That is wild.
It is. And when you cross-plot the active bombardment of the density tool with the active bombardment of the neutron tool, the mathematical separation between those two squiggly lines gives you a highly accurate measurement of the pore space.
That is incredible. Okay, and finally, S on sonic. That one has to be the actual sonar equivalent.
It is. It emits a high-frequency sound pulse and measures how fast that acoustic wave travels through the rock.
And sound changes speed based on density.
Right.
Right.
Sound travels faster through a tight, solid matrix than it does through a porous rock filled with compressible fluids.
So this entire suite of logs, radiation, electricity, atomic bombardment, and sound waves, all of these independent physics experiments are being run simultaneously as the tool is pulled up the well.
Every single one of them.
But the tool isn't handing you a neat little summary, is it? It's handing you raw physics data.
Exactly, which is why the core message of our source material is so vital. A log response is just a signal. The job of the petrophysicist is to connect that downhole response with the physical rock and fluid interpretations we talked about earlier. The tool doesn't know what porosity is. It only knows how many neutrons bounce back.
Which brings us to the most dangerous part of this entire process. Because here's where it gets really interesting.
Oh yeah, the trap.
Yeah. You have all these high-tech tools, millions of data points, and thousands of feet of complex geology. And yet, the source material dedicates a major warning to what it calls the common trap.
It's a crucial warning.
It says, do not let one number carry the interpretation.
It is arguably the single most expensive mistake you can make in this industry.
Really?
Absolutely. Because humans crave certainty. When a drilling manager or an investor asks, what do we have down there? They want a single number.
They just want the bottom line.
Right. They want you to say, we have 18% porosity, but the Earth does not owe us simplicity.
So let's talk about the real-world stakes of that trap. If you just grab that 18% porosity number and run with it, what goes wrong?
Well, if you let that one number carry your interpretation, you might recommend drilling a $50 million well based on that 18%.
$50 million.
Easily. But what if you ignored the gamma ray log? What if that log was quietly showing tiny microscopic layers of radioactive shale interbedded in that sandstone?
Oh, I see where this is going.
Right. That 18% porosity physically exists, but because of the shale, those pores aren't connected. The permeability is zero.
The fluid can't flow.
Exactly. The fluid is trapped. You just spent $50 million drilling into a completely locked vault. It's a dry hole.
Wow. Just because you pulled a number out of context, you let a single math output override the integrated environment.
And this raises an important question. How do we enforce discipline? How do you stop smart people from falling into the trap of oversimplification?
Right, because the temptation is huge.
It is. So the field guide provides a relentless three-step practical review path to force context onto every single claim you make.
Okay, let's walk through them. Step 1. Check how the evidence supports the rock properties control before interpreting the concept.
Yes.
This is the 92% foundational check we talked about. You are basically forcing yourself to prove the physical architecture exists before you make any claims about what is inside it.
Exactly. Do you actually have a reservoir rock, or are you looking at a weird anomaly? Prove the container first.
Right. Then step 2. Compare the fluid behavior and core and logs controls before writing the interpretation statement.
So here, you've proven the rock. Now, do the electrical resistivity logs and the neutron logs actually agree on the fluid behavior?
You're checking the different tools against each other.
Yes. And does the microscopic core data match the macroscopic tool data? You must cross-reference the physics before you write a single word of your conclusion.
You are building a web of corroborating evidence. You can't just cherry-pick the good log.
Never.
And finally, step 3. Use the geological context control to define the practical limit or next review step.
And that is our 68% boundary.
The reality check.
Exactly. You have your conclusion based on the physics. Now you step back and ask, does this physically make sense in this specific geological basin?
Right.
A technical claim must remain strictly limited to what the integrated evidence supports. You don't guess. You don't extrapolate beyond the boundary of the geology.
It really is a profound lesson in scientific humility, isn't it?
It truly is.
You are constantly cross-examining your own data. The ultimate takeaway from this framework isn't about memorizing tool acronyms or running an equation perfectly.
No, it's bigger than that.
The guide explicitly says, understand the rock, interpret the data. You are weaving the container, the contents, the physics of the logs, and the history of the Earth into a single cohesive reality.
It requires immense discipline to hold all those variables in your head at once, but when it works, when all the data aligns, it is beautiful.
I can imagine.
The field guide leaves us with this wonderful summary of the entire endeavor. Rocks tell a story, we learn to read it.
Rocks tell a story. We learn to read it. I love that. We've explored the vocabulary of that story today, the radiation, the acoustics, the atomic collisions.
The whole alphabet soup.
Right. And we've looked at the rigid grammatical rules they use to read it through those cascading percentages. And of course, we've seen the multi-million-dollar danger of taking a single word out of context.
It's a high-stakes game.
It really is. We want to thank you for joining us on this deep dive into the subsurface. But before we let you go, we want to leave you with a final thought to ponder.
It's a good one.
We talked heavily about how geological context, that 68% bounding box, acts as the ultimate reality check. It defines what an interpretation cannot claim.
Right.
But what happens out there in the real world when you get a seemingly perfect, well, log reading like a flawless, scientifically vetted set of downhole numbers that completely contradicts the known geological history of an area?
It happens more than you'd think.
Which piece of evidence do you trust when the physics of the tools and the history of the rocks tell two completely different stories?
That is the exact moment where true interpretation begins.
Something to think about the next time you look down at the ground. Until next time.